So now let us dive into the test tab itself. So the test tab is where the operator builds the actual test procedure, and every test point will later appear inside the test table here, which is created from the setting configured, and also the operator can define the test mode, the voltage and current values, the power angles, and many more parameters. And once the required settings are prepared, they can add directly into the test table by using this button to be executed later on. So the first and the most important section inside the test tab is the test mode selection, as you can see from here. Okay, so the selected test mode defines what kind of behavior the meter module should check during testing. We have different test modes, as you can see, which can be used for different meter function and different verification testing. So the first type, which is L, which means the load test. This is the most commonly used test mode inside the meter module, and the purpose of the load test is to determine the measurement error of the energy meter. So during the load test, the CMC will generate voltage and current quantities and inject energy into the meter under test. A test continues until the meter sends back the specified number of pulses. At the same time, either the CMC itself or external reference meter measures the actual injected energy, and then the meter module compares the measured energy against the expected energy and calculates the final meter error. So this test is extremely important because it verifies the actual measurement accuracy of the energy meter under test against the normal operating conditions, and it's also commonly used during the commissioning, maintenance, and calibration testing activities. The second one, which is the mechanism test. So it's called counting mechanism test in some cases, and this mode is used to determine the total meter error, including both the measurement section and the counting mechanism. So in this test, the operator manually enters the initial meter reading before starting the test, and at the end of the test, the operator manually enters the final meter reading. So the meter module then compares the difference between the two readings against the injected energy and calculates the total meter error. So this test is especially useful for meter where the counting register itself must be verified separately. Then we have the third one, which is injection, called I. So the injection test is used when we want to inject a known amount of energy into the meter for a specific period of time. One important thing to understand is that the injection test doesn't perform automatic assessment or automatic reporting. So the meter module simply generates the required load profile without evaluating the meter response. So this mode is commonly used when comparing multiple displays or remote indicators connected to the same energy meter. The fourth one is the no load test, as N here. So the no load test is mainly used for rotating disk meters, and the purpose of this test is to verify the meter doesn't rotate when no current is flowing. So in the standard no load conditions, the meter should remain completely standstill. So if the meter module detects even one pulse, the meter is considered started to move. However, the meter module also provides another option, as we explained from the setting tab here, which is accept one pulse in the no load test. When this option is enabled, one pulse is tolerated and the meter is still considered not started, and this accounts for small mechanical movement that may occur without representing continuous rotation. So during the no load test, all current are set to 0 from here. So if you select the no load test and if you select any amount of value to be entered here, you can see the current now is 0 because it's no load test, while the configured voltage remains applied to the meter, as you can see from here. Then we have also the creep test. So you can see the creep test now is another important test mode, which is used mainly for rotating disk meters. The purpose of this test is to verify whether the meter starts moving under very low current conditions. So the meter modes applies a small creep current to the meter and check whether the required number of pulses is generated within the allowed test duration. So the software also provides the other option, which is require one additional pulse in the creep test, as we explained before in the setting tab from here. You can enable it or disable it based on your preferences, and this helps to avoid false start detection caused by small mechanical movement. Also, the creep test is very important because it checks the sensitivity and startup behavior of the meter at extremely low load conditions. Now that we understand the available test modes, let us continue with another important section, which is the current waveform. As you can see, sine plus, and sine plus DC. Okay, so the current waveform section allows the operator to define the shape of the generated current waveform. So this is important because modern energy meters may have different behavior under distorted waveforms compared to pure sinusoidal conditions. So the first option is a pure sine wave, as you can see. So when this option is selected, the CMC will generate a clean sinusoidal waveform without harmonics or without DC components. The second option here, which is a sine plus, allows you to add or superimpose the harmonic waveform component to the fundamental sine waveform. And in this mode, the waveform contains both the fundamental frequency and the selected harmonic order from here. So you can simply select between second harmonic up to 20 harmonic for 50 hertz. And this magnitude of the harmonic can be adjusted between 0% and 100%, as you can see from here, of the fundamental waveform. And the harmonic order itself can be selected, as we explained, in third or fifth or seventh harmonic and so on. But there is one important information here, which is the maximum output frequency of the CMC is 1000 hertz. Because of this limitation, the maximum selectable harmonic depends on the fundamental frequency. For example, if the fundamental is 50 hertz waveform, so the harmonic can be set between the second and the 10th harmonic order. But if the fundamental frequency is 60 hertz, as we can see now from the test object, we can change the fundamental frequency to be 60. And you can see now the effect of the harmonic order. So now it's between 2 and 16. Okay, so because we have the limitation of 1000 hertz of the CMC output frequencies. We have also the phase angle or the phase shift of the harmonic can be adjusted independently here, and this allows simulation of many different distorted waveform conditions. So this feature is extremely useful for testing modern electronic meters under harmonic reach environments like the industrial power systems. Then we have sine plus DC. So the third option allows adding a DC component on the top of the sinusoidal waveform. So this feature is useful when evaluating meter behavior under DC offset conditions. Now let us move forward to the nominal box from here. So for the load test, for example, you can see here the nominal. We have here also the actual table. So the nominal section here, it defines the expected value according to the meter specs. And this is the target values used by the meter module during the testing. On the other hand, we have here the actual section, which continuously displays the real measured values during the test execution. Also, there is one important concept here to understand, that the pulses, energy, and the time are automatically and mathematically linked together through the meter constant. This means that changing any value will change the other two values. For example, if I change the one to be number of pulses, now the energy and the time is changed. If you change the energy, it will change the pulses and time, and vice versa. So for example, here the operator can enter a specific test duration, and the meter module automatically will calculate the corresponding pulse count and the energy value required for this condition. Also, the automatic relationship simplifies the test preparation and helps to avoid calculation mistakes during the setup. Also, here we have the supplied quantity. So the supplied quantity field here displays the nominal power quantity corresponding to the selector vector settings, as you can see from the detailed view, as a voltage and current values. So if you change these values, for example, it will change the displayed or the supplied quantity. Then we have the tolerance field here. So the tolerance setting defines the acceptable error limit to be used during the result evaluation. So normally the default tolerance comes directly from the selected meter class, which is 0.5 in our case. However, according to the IEC standard, the acceptable error may also depend on several additional conditions, such as power factor, harmonics, voltage impedance, or the operating points. And because of this, the operator also may sometimes need to adjust the tolerance manually for individual test points. Then we have the test runs, as you can see. So the test run parameter defines how many times a specific test point should be executed. So when multiple test runs are selected, the meter module performs the same test repeatedly and calculates the average values and standard deviation. So the individual results of the latest runs can also be viewed directly by moving the mouse over the result, as we will see in the practical sessions. And also one important optimization is that the setting time here, setting time defined in the test object, is not repeated before every run. So the setting time is only applied once at the beginning, which helps to reduce the unnecessary testing time. Also, we have here the pause button, as you can see, and this pause test option allows the operator to temporarily stop the automatic test sequence before executing a specific test line. And this is extremely useful during the multifunctional meter testing, where the operator may need to reconnect pulse output on a different pulse LEDs, for example, from the kilowatt hour LED to the kilowatt hour LED, or to modify hardware connection between the test points. And when the test pauses, the meter module displays a message and audible signal to attract the operator attention, and then the test continues only if the operator confirms the action or after the configured trigger condition is satisfied. Now let us move forward to the buttons which used to manage the test table. Here we have the define trigger option. So it will open a dialog box when the operator can define the pause message and the trigger condition required to continue the test. Then we have here the add button. So once you specify the number of pulses or the energy and the time, you can add this test point, as you can see. So here is the mode L, which means it's used for the load testing. Also, you can remove this test line later on to add a new test line, or by double click this test line, you can update these values. For example, if you can change the test runs to be 2, then you can click update. Now the test runs now is 2, which means it will display the average deviation and the average error at the end in the generated test report. Also, you can use this remove all. If you have a multiple test lines or a multiple test points, you can clear all the complete test table. Then we have the box, which is a balanced three-phase system. So the balanced three-phase system section is used to define the operating quantities for a balanced three-phase testing. Also, we have here the voltage line to neutral, which defines the phase to neutral voltage for sure. Then we have also the line to line voltage, which is used to define the phase-to-phase voltage. And also for a single phase meter, this field is not used. So if you select the meter type or the meter test object to be a single phase, so the line to line will not be activated anymore. And then we have also the current, which defines the current per phase. We have also the power angle, which defines the phase relationship between the voltage and the current. Then we have also the frequency, which is the nominal frequency or the system frequency. Then we have also here the eye creep, which will be enabled. If you enable the creep test, now you can specify the creep current, and this is used only during the creep testing and to define the creep current as a percentage of the nominal current. Also, we have here the cosine phi, which is the value of the power factor. Depends on the phase relationship between the voltage and current. And if this power factor is not unity, for example, if it's 0.9, here you can define the load to be inductive or capacitive. So this selection also to define the load type used during the testing if the power factor is not unity. But if the power factor is unity, so this field will be inactive.